Now, in the last hour, we derived the non-homogeneous wave equations. Left-hand side is the wave equation, and the right-hand side are the sources. What sources we have? Current densities and magnetizations. And I am going to show you how we are going to solve this. You know how to solve because you know that the Green's function and non-homogeneous wave equations could be solved easily using the Green's function. So let us do the same thing what we have done last time. So let us take this term, for example, and take the scalar product with the R head from the left. So in both sides, so that should be minus R dot curl of current density plus curl of magnetization. So this comes to in, so that becomes R dot Laplacian H, actually H prime, so this should be the prime, because in Maxwell's equations we convert everything in terms of primes. The other one, K square R dot H prime. So do you remember that what we have done 2 days ago? For that term, what we have done, what we derived? R dot Laplacian of H prime was equal to what? If you look at the lecture notes, that is nothing but Laplacian of R dot H prime. So I do this in full detail. I don't want to do it again. So basically, left-hand side of the equation will be Laplacian plus K square R dot H prime. And what is this? If you call this a new vector, let's say A prime A, not a vector potential, new A. What is this? Do you remember also what we have done for that? Minus R dot curl of some A, not a vector, but some any A. What is this? What we said? That was equal to epsilon ijk del j ak, and this is ri. You have the minus sign. You can take this to the inside. That is equal to epsilon ijk ri del j ak. You can flip this 2 times with 2 minus signs, it makes positive. And that is nothing but, what is this? If you take the k to the here, that is nothing but, that becomes k I j, and that is nothing but R cross gradient dot product A. If you multiply by I, divide by I, one of them will be the angular momentum operator. Okay? So basically, right-hand side will be minus I L dot J cross or J plus curl of magnetization. So we take the vectorial equation, which has 3 components, using the property of R dot Laplacian is equal to Laplacian of r dot h prime. This is working with the property of the del dot h prime is equal to 0 if you look at the notes. And the right hand side could be written L and the other terms. So this is a scalar wave equation. If you do the same algebra for the other one, you will obtain another scalar non-homogeneous wave equation that will be r dot e prime with the source terms Z0 k L magnetization 1 over k square curl of current density. So what is the solution? The solution is simply we studied. We said that if we have a non-homogeneous scalar wave equation, the solution, so which depends on, let's say, x, the solution should be in the following form. Phi of x should be Green's function x prime times the source integrated through the volume. And the Green's function gx x prime is e to the ik x minus x prime over x minus x prime. Okay, this is for any non-homogeneous wave equations. So we have the same situation here. Basically, the solution only one term will be very simple. So, for example, this one, r dot h prime will be 1 over 4 pi with minus 1 over 4 pi because this is divided by 4 pi, minus 1 over 4 pi. Green's function e to the ik x minus x prime divided by x minus x prime times the source. Source is IL current density plus curl of magnetization d cube x prime. If you do the same thing for the other one, r dot e prime will be, in that case, divide to the minus 1 over 4 pi. Green's function times the source Z0 k L dot magnetization 1 over k square curl of the current density integrated through the volume. So this will be the source. Now the next thing, what is our main major aim? This is the solution with in terms of the source and the Green's function. But our aim is what is our aim? What I told you that last time, you have the solution in general E and H in terms of some multiple moment coefficients. So I said that H could be written as what? Summation through the Lm A E Lm FL X Lm I over K AM and E are depending on Lm, curl of GL, KR, XLM. Similarly, you have the same structure for the full electric field. What does it tell us? This is from solution of the non-homogeneous wave equations. And that is the full solution. That is the full solution. And that solutions has orthonormal bases and some coefficients. How you are find these coefficients? You can find these coefficients with the orthogonality conditions. What was that? Let me do one of them. For example, AM, LM. I derive for one of them. That was K of square root of L plus 1 GL KR. Y LM complex conjugate R dot H prime integrated through the solid angle. So for that case, what we know that the R dot H prime from the non-homogeneous wave equations, solution of the non-homogeneous wave equations. And if I plug this information and carefully take the integral, I can find that the coefficients for any zone, because there is nothing here for any zone. It's not a far field approximation, but you can go to the far field also. And similarly, if you want to try to calculate the A sub E LM, you will find 1 over minus K over square root of L plus 1 over Z0 FL KR, and that will be YLM complex conjugate, and this will be the R dot E prime integrated through the solution. So basically, the situation is the following. You know that the fields, total fields, what fields? Multipole fields is a full limb. You don't know the coefficients. You can find the coefficients from here. And another thing, you know that the distribution of the radiation for each multiple order LM, we studied this. We have a feeling what is what. For example, L equal to 0 should be monopole, L equal to 1 is the dipole, L equal to 2 is quadrupole, and it goes. And next thing is this calculations. So I am not going to do these calculations because it will take another 2 hours. That will be a homework exercise for you. So do this and try at least one of them in exactly what are those. But when in your derivation you have, if you follow your book, you will have 2 regions. Once you will go to the far field zone, KR will be greater. The other will be the source dimensions will be the small. That will be the X, K, X prime will be the small. X prime, the dimension of the source will be small relative to the wavelength. And you can find this. And if you find this, you will find, interestingly, you will find the following. For example, for one of them, let me write. Don't derive for both. One is enough, one particular mode. Then we will do applications. One particular form will be the, for example, this one could be written in terms of some coefficients here. You will derive this. One term will be integrated d cube x prime RL charge density YLM complex conjugate plus another coefficient here and another integral. The other integral is more complicated, but the first term is easy. Y Lm complex conjugate divergence of R cross magnetization. So these are in your book. So basically, when you do this, exactly the case when Kr much greater than 1 and Kr prime much less than 1, and do the steps, do the fine calculations. So doing all steps, you will see that the one term is this, and this term you are remembering the multipole moment of the electric field from the chapter 4 in the first part. This is more complicated, so this is related with the magnetization. So basically, if you have a source, an antenna, for example, or whatever, or some distribution of charges, some distribution of the charges. If you go to the far field and if you investigate these coefficients, you can determine what actually is the form of the source, okay? Because you can find these coefficients. You can calculate the L00, L1, M1, 0, 1, so all coefficients, and that tell you that what kind of source you have, okay? So application is much more easy because you will have some definition of the open form of this in terms of the known things like electric quadrupole moments. And when you calculate these electric quadrupole moments, you will calculate that the coefficient. If you know that the coefficients, you can have the information about what kind of the source. So this is the idea for the multipole expansion. Using the fields, you can deduce what kind of source you have at very long distances. So I will stop for the radiation at this point, and I want to start scattering. So particularly, you have one serious homework to determination of at least one of these coefficients, and the other will be the application. So try to complete this section in your book. You will find this if you look at. That is section 10 in chapter 9. And derive at least one coefficient. And as an application, maybe one of them will be solved in the classroom, and the other will be as an application, chapter 9, question 14. This is a single loop, single circular loop, and there's an oscillating current. You will find that the multiple order and multiple coefficients. So that will be a nice exercise, and another exercise will be done in the classroom in the recitation hours. So derivation is homework. So derive one of those coefficients. Now let us try to start the new chapter, that is the scattering. So we will study the scattering basically at long wavelengths, means that the source dimensions is small relative to the wavelength of the incident electromagnetic wave. What we are learned here, we will learn why the sky is blue, that is Rayleigh scattering, and we will learn how we can calculate that the scattering cross sections, such as Thomson scattering cross section. That is a scattering of the electromagnetic waves from the electron. So basically, in the new chapter, our aim will be the following. We will have the source source some dimension d, and there is the incoming wave, and the wavelength is much longer than the size. If the wavelength is less than the size of the source, that is a different regime that is related with the geometry, because there will be reflection, shadowing, and such other things. So this is a good. This will be a good example, a scattering of the electromagnetic waves from the, for example, air molecules in the air, for example. That will be. So the idea is related with the radiation. If you have an incident electromagnetic wave, it has some propagation direction and E and H fields. And if you are a material, very small size, that could have some material structures, let's say that could have electric permeability and magnetic permeability, let's say some. And what happens when the electromagnetic wave interacts with this material? Due to the field of the electric field and the H field of the electromagnetic wave, this material will be polarized as a electric dipole or magnetized as a magnetic dipole. Since the fields are oscillating back and forward, these polarized dipoles will oscillate. So basically, you can have some here a dipole oscillating with the same frequency of the incoming wave, and also magnetic dipole oscillating with the same frequency with the incoming electromagnetic wave. And once the dipole starts to oscillate, it radiates. And this radiation will be treated as what? Scattering. So that will be the first approximation. Okay? So scattering is related with the radiation. So electromagnetic waves induce oscillating electric and magnetic dipoles, and they radiate, and we will try this radiation as a scattered fields. Okay, so you have an incoming fields, and then you will have scattered fields, some mutually orthogonal H and E and H fields, and we will take these fields as a scattered fields. So let us try to do it. So how we can write for the scattered electric field? What we can write for the scattered electric field? So in the previous chapter, we have seen that the radiation of the magnetic dipole, electric dipole, okay, sorry, radiation of H due to the electric dipole C k square over 4 pi n cross P e to the IKR over R. So can you find this in your notes already? This is, yes, that's correct. If you have an oscillating electric dipole, some frequency omega, this is the H field. You can calculate the electric field. What is the electric field? Electric field of the radiation is impedance of the free space, H cross N, and that is nothing but this one. And Z0 is square root of mu 0 over epsilon 0 and the other terms C k square over 4 pi e to the I k r over r n cross p cross n. This will be the field of the radiation of the oscillating electric dipole. Now I will take this as scattered field because incoming electromagnetic waves induce oscillations, and that oscillation creates a, if the medium has some electric permeability, then that will create a oscillating electric dipole. And since I have an oscillating electric dipole, that means that I have a radiating field due to the electric dipole. And if you arrange the coefficients, what you are going to obtain, C is 1 over square root of mu 0 epsilon 0. This term will be cancelled, and that will be 1 over 4 pi epsilon 0. So basically, the coefficient will be 1 over 4 pi epsilon 0, and the other term k square, and this is e to the kr, ikr over r, and the leftover term n cross p cross n. Okay, so we will treat this as a scattered electric field. Now you can tell me that what happens to the magnetic dipole? Yes, there's a magnetic dipole also, depending on the material here. So I know that the radiation from the magnetic dipole. What is this? For the magnetic dipole, the electric field, if we have oscillating magnetic dipole, the E field is minus S0 4 pi k square n cross m e to the ikr over r. So e to the ikr over r is the common. K square is common. This k square is important. I will discuss this through the course, this chapter. That is very important. And we have Z0. Z0 is square root of mu 0 epsilon 0 if you multiply by epsilon 0 square root of and epsilon 0 square root of 2. So this will be 1 over epsilon 0. You can take the parentheses. This will be 1 over 4 pi epsilon 0. You can take the parentheses. You have the k square. You have the spherical wave term. And left over, square root of mu 0 epsilon 0 is nothing but 1 over c. And you have n cross m over c. So let us erase the pieces from the previous work. So this whole stuff has the source of the oscillating electric dipole and magnetic dipole. They are radiation fields, but we will take this as a scattered fields. And I know that for these scattered fields, H will be what? Orthogonal to the E and the propagation. If you want to calculate that the power emission, you have two options. Either it goes as a H or it goes as a E square. Since they are spherical waves, it is everywhere. So 1 over r square and r square will be cancelled. But you are seeing an important thing. If you took this, take the square of this, this k square will be k to the fourth. K to the fourth is what? Omega to the fourth times c to the fourth. Omega to the fourth tells you that if you have higher frequencies, you have more scattering. So basically, this will be the argument for the blue sky. Higher frequencies will be scattered more. This is coming from here. So we will count this later, not today. Now, this is the scattered electric field. We use that radiation approximation. You can easily calculate that the, what would be that the scattered magnetic field, that is simply n cross E scattered over impedance. We did several times this. Now what we needed for the scattering, we need a scattering cross section. So the scattering cross section, sigma is the scattering cross section per salt angle. If I know that the scattering cross section per salt angle, I can integrate through all salt angles. I can calculate the total scattering cross section. So basically, what should be inside the scattering cross section per salt angle? You should have incoming direction of the wave and outgoing direction, and something inside we will be deal with what the other thing will be that the polarization. So if you have unpolarized waves after the scattering, you can see some polarization. So suppose that unpolarized waves towards to you and scattered 90 degrees. So it is unpolarized when it travels to you, but if it is propagates perpendicular to your view, that will be polarized. So there will be terms related with the polarization, incident polarization and the polarization after the scattering. So how we can define that the scattering cross section per salt angle? For incoming wave, you have the power distributed all surface, all flat surface. If you look at the power or infinite surface, you will have the power per area. After the scattering, you have spherical waves. Then after the scattering, that means that you have power per salt angle. So if you take the ratio of this, what is the unit of the ratio? Power and power energy rate. And this goes up area, this goes down as a salt angle. So basically, the definition of the scattering cross section per salt angle is nothing but area per salt angle. So the definition is the following. For incident wave, you have a power per area and 0 dot E incident cross H incident complex conjugate. After the scattering, you have power per salt angle. Real part of R square and dot E scattered cross H scattered complex conjugate. And if you calculate that the total scattering cross section, What is the unit of the total scattering cross section? Dimensions. Area length square. So this is the basic idea. Incoming waves are what? Plane waves. They have power per area. And scattered waves are what? Spherical waves. They have the distribution power per salt angle. And that ratio is related with the scattering cross section per salt angle. And if you integrate this through all salt angles, you will get that the total scattering cross section. So maybe I can write this is more elegant form. Now, let me calculate this term, for example. Determine it down. What is the E incident? E incident. It has some arbitrary direction of unit vector and some polarization. So basically, I will define that the polarization in the following content. In general, that could be a complex number. Because we know that for the circular polarization, we need a complex numbers. In general, it's a number, it's a complex number. Vector, it's complex vector. So, for example, for circular polarization, what was this? That was epsilon 1 plus I epsilon 2. So epsilon 1 is the x, this is the y hat, x hat plus y hat. Or that's one of them left-handed, the other is the right-handed circular polarization. So E incident actually what? Some E0 incident times E k dot x minus omega t. So basically, I'll call that the E incident as a, so this is the plane wave term. I'll take that the coefficient of this as a projection of the E incident to arbitrary polarization. So that is a, in general, a complex quantity, and we are trying to put the polarization in our calculations. So, and 0 dot E incident cross H complex conjugate, cross product H complex conjugate will be the following. And 0 dot E incident cross H incident complex conjugate will be the following. And 0 dot instead of E incident, and 0 is the propagation direction of the incoming wave. E incident is E0 dot E incident. Actually, yes, along any arbitrary x, cross product H. What is H? H is N0 cross E incident over impedance, so that will be N0 cross epsilon 0 complex conjugate dot E incident over Z0 along X set. So let us summarize the things. I defined that the E incident has some direction. So basically you have N0 and E, and you look at the some projections around epsilon 0 of this. These are orthogonal to the propagation direction. So has some direction x hat, and N0 dot E incident cross H incident, which we needed in the definition of the scattering cross-section per solid angle. And I write that the E incident, and I write that the H incident complex conjugate. So if you take the double cross product, what you are going to obtain? This will be A, B, and C. A dot C, X dot X will be unity along N0. So that first term will take N0 dot epsilon 0 E incident dot times E 0 complex conjugate E incident complex conjugate X dot X divided by Z0 along N0. That will be the first term. What will be the second term? What will be the second term? This is A dot C along B. The second term will be what? A dot B. What is A dot B? The first term is A dot C. If you say that this is A, B, and C, the first term is A dot C along N0. The other term is A dot B. So N0 is the propagation direction. X hat is a unit vector of the electric field along the polarization. Basically, 0, it is perpendicular. Propagation direction and the polarization are perpendicular to each other. The other term will be 0. And if you take the N0 dot N0, that will be 1. And this is 1. You will left with that term. So I'll write the result. I can derive this again in the next time. So this will be 1 over 2 Z0. What is this? Epsilon 0 dot E incident square. And if you do the same algebra to above, you will obtain 1 over 2 Z0 R square. The square, in that case, you will take that the scattered field and projection to the polarization after the scattering. So I am going to do these things again next time because we go quickly, we haven't much time. Basically, I show you that how you are take into account the polarization. You have the polarization before the scattering, and there will be polarization after the scattering. So if you do this calculation, you will end up with the E incident dot E0 square. And if you do the same thing, the above term here, nothing will be changed. Instead of H scattered, you will write A scattered as a n cross E over impedance and do the same algebra, then you will have the following term. The scattered field dot product polarization after the scattering times the R square. And this whole stuff will be the scattering cross-section per solid angle. So I will go over the derivation next time, and I will calculate that the total scattering cross-section for a electric dipole or for a conductor, and I will continue. And so that's all. So we can stop for today.